speaker of today is Francesco Dept from the Department of Control and Computer Engineering. He will give a speech entitled Assessing the Effectiveness of Enhanced Virtual Reality Systems for Accurate Robot Teleoperation Tasks. Francesco received the Master of Science degree in Cinema and Media Engineering from Politecnico di Torino in 2016. He is a PhD student at the Department of Automatica and Informatica of Politecnico di Torino under the supervision of Professor Andrea Sanna. His research interests include human-computer and human-robot interaction, augmented reality, and virtual reality. He is particularly interested in applying virtual and augmented technologies with industrial robots to improve the human-robot collaboration area. Please, Francesco.
Okay, thank you for the introduction. I'm just going to share my screen. Okay. Okay. Hello, everyone. I'm Francesco Dept, and today I'm going to talk about one of our last research projects called Assessing the Effectiveness of Enhanced Virtuality Systems for Accurate Robot Teleoperation Tasks. This project has been done in collaboration with two other departments from New Zealand, the Emphatic Computing Lab from the Bioengineering Institute, and the Department of Mechanical Engineering. This year, I spent 6 months in New Zealand, and I had the opportunity to collaborate with them. Specifically, the Emphatic Computing Lab is specialized in the development of mixed and virtual reality interfaces, whereas the Department of Mechanical Engineering is specialized in the robotics and automation areas. Let's say I worked as a bridge, sort of bridge between these two departments, trying to develop virtual reality interfaces to control robotic arms, such as the one displayed here. So let's start from defining what is an immersive virtual reality interface, and then we'll move towards the so-called enhanced virtual reality ones. So virtual reality interfaces, VR, is an interface that allows users being physically present in a non-physical world. Normally, one of the most common devices employed to develop, to experience immersive interfaces are the head-mounted displays, as shown in this picture here. These devices are equipped with motion sensors that allows to compute the head rotations in terms of yaw, pitch, and roll, whereas the position of the head is normally tracked using external tracking sensors. In addition, in order to interact with the virtual environment, normally the manufacturers provide controllers, 6 degrees of freedom controllers that basically allows to compute the position and orientation of the hand in the 3D space. There are several types of controllers from different manufacturers, and also special gloves that allows to basically compute the position and orientation of each fingers. Let's say that this kind of interfaces has been quite researched in the telerobotic field. Basically, there is a sort of shift from the so-called pre-modeled environment towards the real-time scanned environment. With pre-modeled environment, I mean that the robotic cell and the factory have been pre-modeled using CAD software such as Blender, Maya. I don't know if you're familiar with. So basically, there is no real reconstruction of the real space. Whereas then after that, there's been a shift toward the pre-scanned environment, as shown in this video here. Basically, the factory or the robotic cell is scanned using dedicated sensors such as RGB depth cameras. And basically, there is a sort of one-to-one match between the reconstructed environment and the real one. But again, it's done offline. Everything is done before interacting with the environment. Let's say nowadays we are instead moving towards real-time scanned environment, and we'll see them later more in depth. But basically, they exploit the same technologies of the pre-scanned environment, so these RGB depth cameras, but they this environment use these cameras to capture in real time the real environment that is streamed over the network and reconstructed in real time at the user site. But what is important to stress is that independently of the environment, the operator can control the robot using the immersive VR device, as shown in this picture here. Basically, you are immersed in the virtual environment. You can, for example, virtually grab the end effector of the robot, and you can move it around. The other concept is that the virtual and the real robots are coupled through a digital twin. A digital twin is basically a strong link between the real and the virtual robot. Basically, for example, when the robot moves towards a specific direction, the virtual one moves accordingly and vice versa. So regarding the last, the real-time scanning environment, basically, as I said, the environment are characterized by the acquisition of the real environment in real time using sensors. The data is transmitted over the network and reconstructed in real time, and the operator can control the robot using an immersive VR device. As shown here, this is a research paper done by MIT. Basically, to give you an idea, the user is immersed in the virtual environment. Everything you are seeing here is captured in real time using RGB depth cameras. That could be, for example, the Kinect sensor. And then you see that the user is virtually grabbing the end effector of the robot, and the real one is moving in real time. And this is the camera that is positioned in front of the robot in order to capture the environment. And I will refer to this kind of system with the term enhanced virtual reality system, EVR. Usually, these teleoperation systems are employed for pick and place scenario, as shown here. Basically, pick and place means picking an object and moving toward a desired goal, but the trajectory between the two poses is not important. Instead, there is a lack of studies that analyzes the effectiveness of the VR interfaces for robotic tasks that require high accuracy, such as surgery, welding, and painting. These kind of tasks are characterized by, the trajectory between points is really important. So we try to evaluate this kind of interfaces in such tasks. In order to do so, we develop our custom solution of EVR framework. This is just a high view of the framework. Basically, it's characterized by two different environments, the local environment and the remote one. The local environment is composed by a real universal robot UR5 and two IntelliSense D415 cameras. These cameras basically can capture both RGB information, color information, and depth values. And they basically reconstruct a 3D representation of the real environment. We develop a custom solution to stream the camera frames over the network towards the remote environment. In addition to the camera frames, also the joint configurations of the robot are streamed in order to establish a communication between the real and virtual robot, the so-called digital twin. So all these data are streamed all over the network and basically used in the remote environment. By using an immersive virtual reality device, the user can see the reconstructed environment and the virtual robot that moves in the same manner of the real one. And on the contrary, on the other direction, we send the pose of the pose means in terms of the position orientation of the joystick on the network in order to control the end effector of the robot. in order to analyze the effectiveness of such interfaces for accurate robot tasks, we compared 3 different kinds of interfaces. The EVR, another one is called EVRR, that is basically an EVR version with a CAD model of the robot superimposed on the real one. With this, I mean, if you see here, this is the EVR, so everything is captured with the cameras. EVRR is this one, where you see everything is still captured with the cameras, but you see that there is a virtual representation of the robot superimposed on the reconstructed one. This is the reconstructed, it is hidden behind. We did this in order to understand whether the visualization of the robot could improve the control of the robot itself. And the other one was a pure classical immersive VR interface, a pure VR, where you have a nice representation of the robot, but basically you lack all the information regarding of the surrounding of the robotic cell. And this is the real robotic cell. So you have to imagine that we place the Intel's real sense camera in front of the robot, and they are capturing the environment. And this is stream over the network towards the remote environment when the user can interact with the immersive VR device. This is a small video showing the EVRR interface. So, so basically, just to explain to you, this is me. The central video is showing what I'm seeing. This is me, and this is the real robot. Basically, as you can see, you can freely walk inside the virtual environment. You can also teleport. Basically, you can teleport whenever you want because it's virtual. And then by using the joystick, you can control the movement of the robot. As if you notice, when the virtual robot moves, the real one moves accordingly. And basically, we try to understand whether this kind of operation is suitable for accurate robot tasks. Yes, so in order to do so, we involved 18 users, and we asked them to perform 2 different kinds of tasks, pose task and speed task. Pose tasks are characterized by, basically the users had to position the real and the virtual, of course, a robot end-effector. With end-effector, I mean the last part of the robot arm. They had to position the end-effector in a very specific position of the 3D space, and this position is highlighted using this virtual asset here. So basically, they have to move it in this position. And this is for the pose task, while the speed task, during the speed task, the users, it's this one, the users have to move the robot end-effector along a very specific trajectory highlighted in purple with a very specific velocity. To do so, basically they had to match the position and velocity of this green asset here that is moving along the trajectory. This is what's one of the tasks they had to carry out. And basically we collected 2 different kinds of data, objective data and subjective data. Objective are the end-effector pose for the PT task and the end-effector trajectory of the ST task. I forgot to mention that for both pose and speed task, both the goal poses and the trajectory have been pre-recorded with the real robot to ensure a common baseline. And we also analyzed the subjective data. During my research, I'm mainly interested in the human-computer interaction, so we stress to analyze also the user performance, not only the objective data, but also the subjective one. Oh, sorry. To do so, we analyzed the usability and the workload of the interface by using 2 well-known questionnaires, the System Usability Scale Questionnaire and the NASA Questionnaire. In addition, we try to evaluate the attention, spatial situation, and presence of the interface. That means whether the visualization of the interface, the robot and the surrounding could affect the effectiveness of the interface. These are the main results. I try my best to explain. Basically, they are divided in pose, speed, and questionnaire results. The pose, basically, the green are the best results, yellow the average, and the red the worst one for all the tables. Basically, when you see something like VR, EVR, and there is a sort of value equal or different to 0, there should be something. It means that there is a statistical significant difference between these two kind of interfaces. So to give you an example, for the first task, VR, this number are the sort of errors. Lower is the result, better is the interface. So the VR perform better, followed by EVRR and EVR. But what is important is that we could only detect statistical differences between VR and EVR and EVRR and EVR. And this, let's say, apply for basically all the results. This means that we can be really sure saying that the EVR interface is not the best one, actually it's the worst one, but because both VR and EVR are better than this, but we cannot say nothing about the differences between VR and EVRR because there were no statistical significant differences. So it means that they can be the same. Generally, VR performed better for mostly all the tasks, but for, of course, the spatial situation presence section of the questionnaire, because since the users could not perceive the surrounding of the environment, they could only see the robot. Basically, they couldn't understand where was the location, where the operative area, and so on. These are just some considerations. So generally, VR is the best one, but unfortunately for both VR and EVRR, which were the best, the errors were still in range of 1 centimeter, which is still insufficient for a high precision task like welding. We need to improve the control algorithm. What is clear, I think, is that EVR is not adequate to control robotic arms. And this is quite contrary to the common state of the art, because for pick and place scenario, no one detected any anomalies, but for high accuracy tasks, it seems there are. Because the EVR interface, the pure one, carries artifacts. With point cloud, I mean the visual in point cloud are the data carried by the EVR interface. And if you see, there are artifacts because close to the edge of the objects, basically the resolution of the camera is not enough to clearly basically the background and the foreground are rendered the same level. So there were some sort of artifacts that really negatively affect the visualization of the robot. And moreover, the point cloud by nature is not stable. It changes every frame, generating unstable virtual meshes. So our future work had to improve the point cloud visualization and the related streaming by applying machine learning techniques to recognize the real objects. Imagine being able to recognize the table, the objects. Once recognized, you can replace them with their CAD models, stabilize the visualization, and reduce the data transmitted of their network. And of course, we'll try to improve the control algorithm, try to tune the mapping between the movement of the user's arm and the displacement of the robot and the effector. Yes, and these are some pictures from New Zealand experience where I spent there 6 months this year, and this is me in the lab with one of my friends where we were developing the system. Yes, this is it. Thank you for the attention.
Thank you, Francesco. We have a few questions for you. The first one is, you have shown that you can drag the robot at the end effector, and the robot reacts with its own kinematics. Could you use several sensors along the arm of the user to capture more data, and do you think this will improve performance?
Well, okay, let's say, I'm just looking for the slide.
Yeah.
Okay, maybe, okay, to improve the control, you can, of course, add sensors to improve the control of the end effector. But what we would like to try is not adding more sensors to capture data related to the position of the user's hand, but to the robot itself. Basically, if you can add, for example, proximity sensor to the end effector, trying to understand the distance between the end effector and, I don't know, an obstacle. So basically, it could reduce the speed when the robot is approaching towards the surface. So try to develop an interface that is not completely controlled by the human, but I will call it such as a percentage control. Basically, the user can say, okay, robot, you can do whatever you want, you have total control. Or I can say, maybe I have 40% of the control, it's up to me, and the 60% it's up to you. Try to collaborate with the robot to improve the control itself.
Okay, so this would mean that the user has more feedback from the robot.
Yes,
this is
exactly.
The increase in data is one directional.
Exactly.
Okay. The next question is this kind of interface already more precise than using only a joystick and a non-immersive screen?
Okay. Yes, I mean there's been quite a lot of research in this area. Basically, what appears is that in this work we didn't compare to a common video interface, because we already know that with just a video interface you lose the perception of depth. It's really difficult moving the robot not in the horizontal plane, but I mean not in the vertical plane, but in the horizontal one. Whereas using immersive interface, since you are there in a 3D world, you can freely move around and see the task from all perspective you want. And this is far more better than controlling from a common video one. For this reason, we didn't compare it with a video interface, because we already knew that is some way superior than the other.
Okay, thank you. And the last question is asking for some applications for this VR technology.
Okay. Yes. Okay. Application could be, if we improve the control algorithm, I mean, could be, for example, this freak here, surgery, welding, and painting. For example, painting is for cars. Imagine is shown here in the picture. Basically, you have to be enough precise to paint the car parts, but not so precise at 1/10 of millimeter, because these robots are really precise. But for several type of applications, it's not necessary to be so precise. And so painting is one of that. For welding, basically you can also teach the robot the movement, because another kind of task that is normally done to teach the robot sort of movement. Normally the approach is the so-called kinesthetic approach. With the kinesthetic means you physically grab the robot and move it around, and the robot memorizes all the poses and trajectories. This is good, but it's not so, it's really slow. And it has been demonstrated that using virtual and augmented reality interfaces, you can achieve better performance in with lower time. So yes, I mean, I think you can teach the robot. The objective is teaching the robot a sort of new movement for this kind of task here: surgery, welding, and painting.
Okay, thank you very much.
Okay, thank you. I stop sharing.
Yes, thanks.